Hello students, welcome back for nuclear physics classes. I am Abhishek Kumar Chowdary, physics lecturer at Sri Chaitanya Gosala campus. See, we have almost finished the nuclear physics. The entire discussion was quite interesting, quite conceptual, quite numerical as well. But there was a limitation that we had to be inside the syllabus of nuclear physics that is given to us, that has been given to us by the NTA. Now, I'm going to summarize the entire discussion of nuclear physics. This is the synopsis class, a quick revision class. Let's see the points we are going to discuss. Note it down. If you're comfortable, it's okay. If you're not memorizing the point, go and memorize them, study them, revise them one more time. Okay, but I'm very sure you all have revised it. So, starting, if you remember, we started our journey from where? We started our journey from Rutherford's experiment. Okay, Rutherford experiment, nucleus was discovered, alpha particle was bombarded. Nucleus, it was the core of that atom having more than 99.9% of mass of atom. The size was very less, 10 raised to power minus 4 times. At times it is also somewhere written like 10 or minus 5 times also. This is the nucleus doesn't have a solid boundary. Nucleus doesn't have a solid boundary. Okay. And so to define that this is the exact boundary, this is the exact radius is not possible. Maybe when the science will evolve, we will have some different data as well. So it is approximate. So let's start point by point. First point, Rutherford discovered nucleus. In that nucleus, what was there? In that nucleus, proton was discovered first because alpha particles, they were being repelled. It means there was something positive inside the nucleus. After that, in the radiation of that beryllium atom, if you remember, in that a neutral radiation having energy much less than the energy of gamma rays were discovered, and that neutral radiation was neutron. So neutron was free neutron, bound neutron. Free neutron, I told you, outside the nucleus, bound inside the nucleus. Free neutron, time half-life of, if you remember, the average life of 1000 seconds, they were like very unstable, and there was some bound nucleus, more stable than the free neutrons. So we discussed these constituents. This was proton and neutron inside the nucleus. Later on, we discussed what exactly is proton. Then we came to know that proton itself is a nucleus. And what is proton? Proton is nucleus of protium. This proton itself is a nucleus, the lightest hydrogen isotope. You know there are 3: hydrogen, that is protium, then deuterium, and then it is tritium. Tritium is unstable, that we can make inside lab, but 2 isotopes are there, and 2 isotopes, I mean hydrogen and deuterium, they actually exist. But among these 3, 99.985% abundance is of what? Is of proton. Okay, so this was the initial points that we discussed, the composition of nucleus. Then we discussed the atomic mass. What is atomic mass? What is atomic number? That you know now. In general, we discussed also that atomic masses are in general the integral multiple of what? Integral multiple of the mass of this lightest hydrogen atom. Okay. Then the next point, so remember, after the discussion of composition, then we discussed the radius of nucleus, nuclear radius. Again, I am telling you, nucleus they don't have a solid boundary. So to define exact that distance, exact distance is not possible, that is always approximate. So before defining that, there was a radius discussion of R naught A 1 by 3, where R naught was 1.2 into 10 raised to power minus 15 meter. And also we discussed a graph for this, that nuclear radius is the distance where the density of nucleus falls to half. If this is rho naught, at radius it will be rho naught by 2. Okay. Then also we discussed that nuclear density is constant for almost all the nuclei. Density of a nucleus is constant. Constant for what? Constant for almost all the nuclei, and this is of the order of 2.3 into 10 raised to power 17 kg per meter cube. Students, here one point is very important to consider, to recall your concept, that nuclear density is constant for two different nuclei. If there are two different nuclei, nuclear density is constant, but inside one nucleus, the density of nucleons is not uniform. This is, you can see from here, the nuclear radius is even the nuclear density of half, the distance where the nuclear density falls to half. Okay. After this density composition, the point that we discussed was, if you remember, that was nuclear stability. For that nuclear stability, we discussed binding energy per nucleon, then packing fraction, and then we discussed what? Then we discussed N by Z ratio. These are the three parameters: N by Z ratio, neutron by proton ratio, that mainly if you remember that we did in the beta decay. So binding energy per nucleon, do remember, binding energy is not measurement of stability. What is actually measured in stability is binding energy for one nucleon. Okay. So then we discussed, if you remember, you have to, these are the checklist of the entire chapter, the final synopsis. Binding energy was delta M, that was mass defect, into C square. Here delta M was in joule, and delta M into 931.5 mega electron volt. Here delta M was in atomic mass unit, which was 1 by 12 the mass of C12. Okay, so AMU 1.66 into 10 raised to power minus 27 kg. Since binding energy per nucleon is the measurement of stability, binding energy per nucleon, it measures stability, and that stability that we have discussed on a graph that was known as binding energy curve. What was binding energy curve? See, the next checklist point is, this is binding energy per nucleon, and this binding energy per nucleon, the graph was plotted with the mass number, and the graph was something like this. Okay, it was the deuterium, which was the lightest, having the least binding energy per nucleon of 1.1 mega electron volt. Then it was Fe, almost 8.75 mega electron volt. Again, these data, they keep on varying with a very small fraction, so nothing is damn accurate data there. And it was falling to till uranium 7.6 mega electron volt. This was the binding energy curve, in which what we saw there was, see, this was stable. These are the lighter nuclei. Lighter nuclei are trying to go in that stable range, and in that stable range they go by doing what? If you remember, that was fusion. Again, these right hand side, these are also try to go in the range of, that range you have to remember, in which the binding energy per nucleon is practically constant. It was from A is equal to 30 to A is equal to 170. Okay, this was the range. Fine. In this range, This was the lighter nuclei. They were trying to go by fusing, by combining, and energy was released there. So obviously they were getting the stability. That fusion we have done in proton-proton cycle also, in sun also, hydrogen and helium, these entire things was done. But here in binding energy curve, you have to understand that both the left, both the right, they are trying to go to the metal. They are trying to achieve the stability, the binding energy of the middle one, where binding energy per nucleon is practically constant. Why this is practically constant? There is a discussion in this also. But first here, this reaction was also exoergic. This reaction was also exoergic. Both was exoergic. In exoergic, again a checklist point, an important point to note down. Water exoergic reaction. What happens in exoergic? If we are talking about exoergic, it means mass of reactant is greater than mass of product. Binding energy of product is greater than binding energy of reactant, and energy is released. And this energy is called positive energy. Energy is released and that is called positive. This is called exoergic. Okay. So the left and right, they are trying to go to the middle. Okay, fine. Now one point was, what is the meaning that this discussion was, these are going to here in a stable range, practically constant range. This is also trying to go in the practically constant range. So we were discussing that binding energy is not constant exactly, but it's practically constant for A equal to 30 to A equal to 170. Now what do you infer from this? What is the information we are getting from this? This information, again an underline point, students, this is the short range of nuclear force. Now what is that? See, from A equal to 30 to A equal to 170, nucleons are increasing. But the binding energy per nucleon is not increasing in that proportion. This is practically constant. So what exactly is happening there, do you know? See, inside a nucleus, one nucleon is not being attracted, not being exerted force by all the nucleons present in that nucleus. What is happening? Only some nucleons that lies in a particular range, they are applying force. Okay. So this is a short range force, very short range force. Nuclear forces are applicable short range. This is why if nuclear force is not going to change, the binding energy per nucleon is also not changing significantly. So the data that from A30 to A70, it was constant. We can infer that, okay, the nuclear forces are the short range forces. They are not changing according to the number of nucleons. Okay. One more very interesting and again an underline point for you students, this here. In the lighter nuclei, on the binding energy curve, if you will observe there what? You will observe a characteristic maxima and characteristic minima. What will you observe? A characteristic maxima and students characteristic minima. Also, on that maxima minima, we also discussed a thing that when we are talking about maxima here, maxima, you can see these peaks. Like here is helium, these are the maxima, here is lithium. So in maxima, the nuclei are such that in which even number of protons and even number of neutrons are there. And at minima, in lighter nuclei, the nucleus was such that odd number of neutrons and odd number of protons were there. Okay. Now what we infer from this, like from A30 to A70, from the constant, practically constant binding energy curve, we infer, okay, the nuclear force is a short range force. Now why this is not in the right hand side? Why this is in the left hand side? Why the maxima minima? Let me tell you a very important concept. You must note it down, students, that maxima minima, they're actually indicating towards the nuclear shell. Yes, you heard it right. Nuclear shell. See, nuclear shell. like this. If you see here, this is the nuclear energy levels. Nuclear energy levels. And the stable one, like helium, is relatively more stable than the lithium, having the greater maximum binding energy, maxima it is, binding energy per nucleon is a little greater than in compared to lithium. What does that mean? It means helium is a lower energy level of nuclear shell. Suppose in NEET they are asking you a question, the characteristic maxima minima of the lighter nuclei in the binding energy curve indicates, you have to take nuclear shell structure. Nuclear shell structure, you heard it right, there is a shell. Inside nuclear has got the spin like atomic electrons, nucleons have got their shell structure like the atomic electrons. So everything is there. The motion of nucleon is almost similar to the motion of nucleons. So this point was very important. The characteristic maxima minima is actually indicating towards the nuclear shell structure. Okay, so after binding energy per nucleon, and let me tell you that is very important. Binding energy per nucleon curve, the information we got from that curve is very, very, very important for your NEET examination. Okay. The next step towards the nuclear stability, if you remember, was packing fraction. It was a bit confusing. Packing fraction concept is a bit confusing. Many students are literally, they are not getting into the basics of packing fraction. So here in this synopsis, I'm going to explain you the proper basics. See, what is it? When we define packing fraction, we have discussed this is delta M by A, that is mass defect by A. Mass defect, generally we take, what is mass defect? We take, okay, mass of nucleons minus mass of nucleus. Mass of nucleons minus mass of nucleus. It is actually this. And we can write here that also. But in general, it's not actually wrong to write it like A minus M here. But in general, we define here, this is not A minus M, rather mass of nucleus minus A divided by A. If you're writing A minus M, that's not also wrong. Mass defect is same. But you have to think the magnitude, mass is not negative positive. The difference is that much only. But we generally denote this M minus A by A, and this is M by A minus 1. In this, I told you the lower is the packing fraction. Lower is the packing fraction, greater is the stability. And moreover, packing fraction has got 0, positive and negative, all three. 0, positive and negative, all three. So 0, listen, 0 is having a lower packing fraction as relative to the positive, but negative is having the lower packing fraction as relative to the 0. Then what it means, the 0 packing fraction is more stable than the positive packing fraction, but less stable than the negative packing fraction. So this is a kind of relative. Moreover, of the final nail, the basics of packing fraction, one question that is damn important in this. Suppose if I'm saying, okay, packing fraction might be 0, it might be positive, it might be negative. So when packing fraction is 0, is M is equal to A, is, for this I am asking you, mass defect is 0 and is binding energy is 0. This is the question in this. So students, note it down, just take your pen and write it. Packing fraction 0 does not mean binding energy is 0. Packing fraction 0 does not mean binding energy is 0. What does it mean then? It means, see, this is relative. Like in potential energy, if you are saying, okay, the mgh is this potential energy, minus mgh is this potential energy, right? Then what is the reference? Reference is the earth. From earth, you have assigned the value 0 at earth. And from upward, you are taking positive, and downward, you are taking negative. So don't you think that potential energy is defined in the reference of earth, that is earth is the reference point. In the same way, packing fraction has got a reference. Packing fraction positive means greater than that reference. Packing fraction negative is less than that reference. So that does not mean M equal to A. It means, let me tell you, F0 is for carbon 12-6. This is for carbon, carbon 12-6. And if the packing fraction is positive, it means it is a bit less stable in comparison to the carbon. If packing fraction is negative, what does that mean? It means it is more stable than the carbon. So that entire stability is in comparison to the carbon. F0 is given for carbon, okay? So in general, A, you know what is A, that is mass number. A less than 20 and A greater than 200, these are having packing fraction of positive. Okay, so these are less stable as compared to the carbon, and the range, in between range 20 to A 200, what in this? In this, obviously packing fraction is negative. These are more stable than carbon and packing fraction is 0 to the carbon. So my dear students, this packing fraction 0 does not imply binding energy 0. This is a very, very important conceptual question, as well as too good a question for the assertion reason also. So this was packing fraction. Then we discussed N by Z ratio, that was 1 for lighter nuclei for the stability, like for helium. If you will say number of neutron and number of proton, you will get it 2 and 2, and the ratio would be 1, fine. And for heavier nuclei, the ratio N by Z for stable, it is around 1.5, 1.6, fine. Now, after that, we entered into radioactivity. And if you remember, radioactivity was of two types. First was the natural radioactivity, the self-disintegration. And the second that I taught you in the radioisotopes, that the sodium-24 is also radioactive. In carbon-nitrogen cycle, we were discussing nitrogen-13 is radioactive. Some radioactive isotopes, they are being created in the lab also. So they are the artificial radioactivity. So we, as a syllabus of radioactivity, we learned the natural radioactivity. What is natural radioactivity? Spontaneous decay. Radioactive means it is unstable. Spontaneous decay to get some stable product. Relatively stable, let me tell you, it is not absolute. It's not like the radioactive is decaying something. That decay particle was alpha, beta and gamma. So there is a radioactive nuclei, there is a decaying alpha, beta, gamma going to some daughter nuclei as a stable product. So that stability is stable as compared to the parent nuclei. Reaction is not going to stop right there. After that also it will gain back the energy, then again this chain reaction, this goes on, this is in chain, okay. But what important point that you have to remember there, first the characteristics of alpha, beta, gamma, fine. What is alpha? Helium nucleus. Alpha is helium nucleus. In very first class we discussed that, this was the 2019 NEET question also. Alpha is helium nucleus, fine. So let's see, what is alpha? Helium nucleus. What is doing? Ionizing air. Very, very, very great ionization power and very less penetration power, fine. But do you know one thing? Now this is note down point. Just note it down. The ionization power of alpha is not long lived. It's not like it is very durable. After moving through a very few distance in air, the alpha particle lose its ionization power. So its ionization power, again they are very important point, ionization power of alpha, it has got a range. It has got a range. Up to a certain range alpha can ionize air. It's not like alpha is moving and it will keep on ionizing air. It's not like this. Its penetration power is very less. Being a charged particle, it is a charged particle, you know. Then it will be obviously affected by the electromagnetic fields. It affects the photographic plate also. These are the characteristics. Its speed is the speed of alpha particle. You know the maximum kinetic energy of alpha in energy decay. So alpha decay is there, some energy is released. So that energy released in the alpha decay, the maximum fraction of that is being back absorbed by alpha. So alpha has alpha particle, they have got a very significant speed. And what is the speed? Let me write it for you. Speed of alpha speed of alpha particle, okay, the range of 10 raised to power 6 meter per second. Okay. Also, there was one point, ionization power of alpha has got a range. Okay. There were some bullet points for alpha decay. Then it was beta decay. And beta decay, students, was of 3 types. The types were negative beta, positive beta, and electron capture. Negative beta, positive and electron capture. What was negative beta? Let's see. First was negative beta. When we say beta, we are talking about electrons. So where is electron inside the nucleus? I know there is no electron inside the nucleus, but what you should know, the electrons are instantaneously produced and decayed. And how are they being produced? NP conversion, PN conversion. So suppose N is converted into P. So conserved charge, this is 0, this is plus, you need a minus. This is called negative beta. This negative beta comes with some energy and also comes with an energy particle called antineutrino. And don't forget the characteristic of antineutrino. Again, the bullet point and note down points. Antineutrino, first, energy packet. Second, rest mass almost 0. We don't need a mass here in this reaction, extra mass. So rest mass almost 0. And third, the proper function is to provide the spin, nuclear spin, to conserve the angular momentum. Okay? So they see, if we are talking about a nuclear reaction, basically the charge, the energy, the momentum, angular momentum, they need to be balanced. So to balance the angular momentum, the energy packet is there. Also the energy packet, the antineutrino, this is also balancing energy. So the bottom line for you is, antineutrino is an energy packet having rest mass 0 and is used for what? It's used for conservation of energy and angular momentum. See, in beta decay, the energy and momentum conservation law, they are highly violated. So Pauli proposed the entire concept of neutrino, antineutrino, and these particles are there to conserve the energy, because in beta, the Q value is not equal to mass of reactant minus mass of product. Rather, you need some extra energy released there as well, and that energy is released in the form of what? Antineutrino. Okay? In the same way, in a positive beta decay, we will talk about, it will be PN conversion. There is a positron, and along with positron, what is there? Along with positron, there is neutrino. Again, neutrino is giving the spin, and neutrino is providing that conservation of energy and angular momentum. But only why they are antiparticles? Neutrino, antineutrino, you know now they are antiparticles. Why they are antiparticles? Because the angular momentum, the spin is opposite. Suppose one is antineutrino, we will talk about. Antineutrino will give spin so that angular momentum and momentum are parallel. If momentum is up, it will give spin like this, so angular momentum is also up. But neutrino will do the reverse thing. It will also provide angular momentum but in opposite direction. That's why they are antiparticle. So these were the concept of 2 beta. This is only synopsis. I am recalling you the main concepts behind them. You have studied them in the previous lectures also. And the third one was electron capture, the rare one. What was the rare in that? The proton of the nucleus. Proton of the nucleus captures its own orbital electron, and this is like positive beta decay. Positron was emitted. So these were the concepts in beta decay. After that, the mathematical interpretation of half-life, mean life, you have to revise. But these were the theoretical points from the starting to the property of alpha, beta, gamma. This I want you to revise, the theory I want you to revise, and you will excel very well in this nuclear physics. Go through the entire videos again and again, revise it, and happy learning. All the best. 180 out of 180 in physics, 720 out of 720 in NEET. This will be there. God bless you, and my blessings are always there. All the best.